So I'm going to do this one a little reverse. I'm going to talk about what you're going to see on the written, but to be honest, there's 3 written questions. The bulk of this is going to be multiple choice, and the bulk of that is going to be right-hand rules, right-hand rules, right-hand rules, magnetic fields, right-hand rules, so on. It's going to be that. So I'm going to talk, first of all, about the equations. One of the ones that we did is F equals QVB, B capital. This is the one that we use for charged particle moving in a circle. A charged particle moving in a circle. And as an example, click. Oh, heck, let's go with one of the old ones. Sure, that'll work. Blah, 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 blah. This is my old cut and pasted review that I used to use back when I first started teaching Physics 12. I'm looking for a lovely written question here. No. Yo. I'll try to. If you ask me nice, sure. I'll print things. Here. This works. This is from January 1990, back in the day. They had tests back then? Shut up. Okay. Let's do this. Yeah, I'll print this for you so you don't have to try and sketch these diagrams, but I need to make it a little smaller to fit it on the page. All right. It says, as shown in the above diagram, I probably won't give you the above diagram because those graphics are a pain to make. A proton enters a magnetic field at location A. The radius r of the proton's path was 3.25 meters when the magnetic field strength was 2 times 10 to the negative 2 teslas. What's the proton's speed when it entered the magnetic field? Okay. First of all, hey, this is a chance for us to practice our right-hand rule. The proton is starting out at the bottom of the diagram, traveling which way? Hey, let's all of us point our thumbs up the page. Which way is the magnetic field? What do those X's mean? Into the page. So it's going to get deflected right when it hits the magnetic field. It's going to get deflected left, and it's going to keep getting deflected left. And why, yes, it would travel in a circle. Is that okay? Yeah? Yeah. Sure? Yeah. Okay. So I just wanted to, use that as a quick review. You're going to have some kind of a written question where we're pushing into a circle, and your approach is going to be, it's the magnetic force that's moving you in a circle. It's going to be QVB equals MV squared over R.
Jordan Cedar, please come to the office. Jordan Cedar.
Hey, a V cancels. Again, what have I said the common mistakes are? Kids forget the mass. Don't do that. Now, how many variables do you have left? I guess after canceling, I have QB equals MV over R. 5 variables, any 4 give you the 5th. Any one of those is fair game. Usually, I'm interested in the radius because I'm kind of a nerd. But in this question, they're not. In this question, what are they asking me to find? Speed. So I think here I'll have, what, Sebastian? Sure. QBR or RQB over M. They may give you the charge. Please remember, if it's a proton or an electron, you know the charge. 1.6, it is a proton, yes. 1.6 times 10 to the negative 19. Magnetic field, 0.02. That's what 2 times 10 to the negative 2 teslas is. Yes, that's on your formula sheet, that 1.6 times 10 to the negative 19. Yeah?
I know that.
Okay. Radius, they said, was 3.25 meters. And the mass of a proton, 1.67 times 10 to the negative 27. Can you check me, Gabby? Yeah, I'm right? Holy smokes. Like I said, I have these memorized by the end of the year, and then I forget them over the summer, every year. Speed. By the way, I'm expecting something in the 10 to the 6th, 10 to the 7th, 10 to the 5th range, like fast. Stick it around?
No, I forgot.
Okay. Troublemaker. I'll get you next week.
Okay.
Or you could just do the homework. 1.6 times 10 to the negative 19 times magnetic field was 0.02 times 3.25 divided by 1.67, negative 27. 6.23 times 10 to the 1, 2, 3, 4, 5, 6. Okay? Now, the other thing that probably I'll do, if I ask you to find the radius, which to me is the most straightforward one, this would make for a good using principles of physics right to explain type of a question. For example, let's consider, let's do that so you know it's a separate question. The radius. If I got the r by itself, I think r ends up being mv over QB. And so I could ask you a question like, oh, suppose it was an electron. What could you tell me about the radius compared to the previous question? Bigger? Why? Convince me. So a higher mass on the top would give you a bigger answer? You think an electron has a higher mass?
Or a smaller mass.
Smaller mass. So you know what? An electron will be bent faster. It'll be smaller. Okay? That might be a using principle. Or I could say, what if you double the speed and it's a proton still? Radius the same, bigger or smaller? Bigger, twice as big as a matter of fact, because there's no squareds on the V, unlike the energy questions, there's no squareds. Or I could say, what if you double the speed and you double the magnetic field? No change, because you got a 2 on the top and a 2 on the bottom. This is one classic using principles of physics right to explain question where I mix and match, and I can either muck around with the speed and the magnetic field, or if it was an electron, I'll make it a proton, same charge, different mass. Or if it was a proton, I'll make it an electron, same charge, different mass. And also an electron would be deflected in the opposite curve. So instead of deflected counterclockwise, it would be deflected clockwise. That might also be a way I could throw this. I could give you a picture and say, pick which is the most likely path. There are some like that in your homework. As an example, from the I'll do one from the older review. I'm sure I already saw one, didn't I? Sure. Here, number 29 here says, when a certain proton enters a magnetic field, it follows path P. That's this one right here. It gets bent downwards and in a medium circle. If an alpha particle with twice the charge and 4 times the mass, what path will it follow? Well, alpha particles have twice the charge, but still positive, so it's still going to get deflected downwards. So it's not going to be S or T. It's either going to be R or P or Q. Let's see. Twice the charge and 4 times the mass. Let me bring back that equation. Double that, 4 times that. What did you say? The radius is going to be twice as big, so I would be looking for a radius that was twice. You know what? It would be Q. So something like that is also a classic multiple choice question. I think on one of my tests I got a picture, something like that. Let me erase those in here, though, because people are going to freak out going, where'd the 4 and the 2 come from? Okay? Last thing that I might do is I might not give you B, the magnetic field. I might give you a solenoid, which is really the third equation we looked at. So for a solenoid, I can ask you to calculate the magnetic field, or I can tell you the magnetic field, and in the solenoid, there's N, I, and L. I could ask you to find one of the other things. Let me find a good written example of that.
Would that be a big question about the
Maybe, or I might combine it with something else. Let me find an example here as I go hunting. Really, Mr. Dueck? You didn't have any good solenoid questions on your old review? Apparently not. Let's go to the newer, older review, which still had some questions overlapping, I know, but that's okay. Yoo-hoo. Whoop, 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 whoop. Sure, maybe something like 16 as a written. Solenoid has the length, diameter, 500 windings. The magnetic field at its center is 0.45 Teslas. By the way, did we need the diameter in the solenoid in the equation at all? They purely threw that in to give you something else with meters in it, a distance, to try and tempt, because I'm sure if you use that 0.04, one of those answers will appear, except I have a feeling, if I recall on this one, the correct answer was C, and it got chopped off. So let me find a better one. I hope I can. I like number 23. I'll come back to that. Oh, apparently I just ran out. Solenoid, I guess going from memory, Dorothy, I probably won't give you a written where I say, hey, just crunch this. Oh, hang on. Oh, yeah. And again, any two, give you the, find the, well, any three, because there's 1, 2, 3, 4 variables. That's a constant, remember. And if you find a fourth, and on the multiple choice, you'll also have this one. I guarantee, I know it's on there, mu naught Ni, where this is turns per meter. That's how you know it's there. The units that it gives you is the number of turns per meter. It's got the N divided by L divided already and reduced into Lowest terms. Okay? Instead, what you can expect on the written, if a solenoid appears, is something like this, for example. The third equation was the magnetic force on a wire, which was Bill. You know what, Dorothy? That's where you can expect that to appear, because this was when it was in an external magnetic field. It would be great if I, in the picture, hint, hint, gave you a solenoid in the picture, and so you had to go mu naught Ni over L to actually find the magnetic field, and then use that to find either the force or the current or the length.
This is where L's are different, right? Possibly.
Yeah. This, good point, Sebastian. This is length of solenoid and current through solenoid. This is length of wire and current in wire. I swear I have a picture of that somewhere, but I'm blanking out. Let me go hunting. Oh, this is the answers. Sorry, what was that? Let me come back to your question. Let me just, I'm hunting for a picture that I have in my mind. No. Nope. 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 It's not a magnetic force. B is a field, not a force. It's not in newtons. It's in Teslas. So if I ever say find the magnetic force, make sure you're finding an F, right?
Oh,
Right? That's a common mistake. Kids get those mixed up, and it's partly maybe my bad teaching. No. Well, take a look at this here, number 25. In number 25, I'm giving you a wire. I'm telling you the force on the wire is 1.6 newtons. But in number 25, I gave you the magnetic field. I would have no problem, instead of having these X's, putting a solenoid in the picture somewhere, either above it or below it or beside it or something like that, and saying, hey, find the magnetic field. Oh, and find the direction, because you have to use your right-hand rule for a solenoid to figure out which way is north. You had a question?
so how would you find the direction of the current?
I would have to either, I've told you which way the force is. What direction is the force? What does it say?
Is it to the page?
No, read the question.
Oh,
It says 1.6 newtons on the wire directed what?
Oh, up.
Up the page. So you're going to point your palm up the page. Which way is the magnetic field?
Oh, it would be into the page.
Magnetic field is into the page. My thumb is the current, so which way is the current going? To the left or to the right?
The right.
It's got to be going to the right.
Okay.
If it was going the other way, that would yoink it down.
Because the thumb would go in the direction of the current. Right?
Yep, thumb, yep. Okay. I sort of like part of that question. There is a question somewhere where I'm going to use the right-hand rule, but I'll do it backwards. Instead of saying, here's the current, here's the magnetic field, which way is the force? I'll say, hey, I want the force to be up. Which way do I want the current to go? Or I want the force to be north. Which way do I want the current to go? Or I want the force to be right. Which way do I want the current to go? Force, magnetic field, current. Okay? I'll do a bunch of right-hand rule stuff in a second.
Are you checking palms before we write this test?
No, but I used to when there was a provincial exam. I used to have to tell the person supervising the provincial that you guys weren't signaling to each other. Because the very first year, I got a call from the frightened librarian at the time. Your kids have come up with these hand signals. They're signaling answers to each other. I said, what? No, and because I realized the provincial exam used to go in exactly the same order that I've taught you, which meant about an hour in is when they would hit the magnetic forces, because it would start out with kinematics, then forces, then energy, then momentum, then equilibrium, which I haven't done with you yet, then circular motion, then electrostatics, then circuitry. The last 6 questions on the multiple choice were magnets. So I figured out, oh no, they're doing right-hand rule. So I told the supervisors after that. I'll do a bunch of right-hand rule stuff in a second. We come back to that. We're just talking about the written right now. Okay? I did say that there was one that I liked, and this is your hint. This is your gift for showing up. I like number 23 here.
Is that it?
Is that part of our...
You have, I think yours is the first number 34. You'll figure it out when I do this one. In the question that I need to make a little bit smaller, so you don't have this one. This is my old handwritten, hand-pasted, cut and pasted review. Ooh, make it a little bit bigger, Mr. Dueck. Okay? It's different numbers, same question. Mabod, what are they asking me to find in Part B? No, Part B. Sesame Street is brought to you today by the letter B. Okay, so I would start out going, hey, I've done this already a bunch of times. This is kind of nerdily cool. And it's going to be QVB equals MV squared over R. And hey, a V cancels. And they want me to find a radius. So R equals MV over QB. And then you would go walking off to the question. And you would say, mass, it's an electron. Woohoo! Charge, it's an electron. Woohoo! Magnetic field. Oh, they gave it to me. There's the Teslas. But they did not. Give me that. What do they want me to find in Part A? What haven't I used yet that the question gave me? Thankfully, it's after school. You're lucky. Sorry, what? Voltage. This is what we were talking about a couple of units ago, where you can imagine a negatively charged plate, a positively charged plate with a little gap through it right there. And here's our electron falling that way. This is our electron gun. And once it gets through there, it's at full speed. And now it's going to hit a magnetic field. How did we solve that? What I've tried to tell you is the parallel plate question, where you have a charge moving from one side to another. Dorothy, that's exactly the same physics as this, dropping a ball. All of your potential turns into kinetic. It's a conservation of energy. We start out going KE, well, let's do it the long way. We start out going KE initial plus PE initial equals KE final plus PE final. But we recognize, just like when you drop an object to the ground, once it hits the ground, it's used up all of its potential energy, and it's starting out at rest. Kinetic hasn't changed since physics 11. It's still a half mv squared. Hey, there's our v, by the way. Woohoo! Potential between plates was QV. Now you want to find where that's hidden in the electrostatics unit on your formula sheet, because it doesn't actually say QV anywhere on your electrostatics sheet. What it does give you,
Brown, are you in the building?
what it does give you is a definition of voltage. Yes? It says that voltage is equal to energy per coulomb. Well, if I get the energy by itself, I get voltage times coulomb, or QV. Is that all right? Q being charge of an electron. If you're really nerdy, you could get an expression for little v. I would just crunch the numbers at this stage and then plug that. I'd carry it to 4 or 5. I'd write it to 3 sig figs in my answer, then I'd carry it to 4 or 5 sig figs on my calculator and move down to part B. Okay. I like that also because, hey, we're near the end of the year. Good review. Good review. Okay. So, you can expect Bill as a written question, but probably I'll ask you to do something to get B with a solenoid, because otherwise, hello. Well, I'll throw, and you know what? Probably be a right-hand rule application here. I'll give you some kind of a picture, and I'll say, now that you know the force or the current, or it's either going to be which way is the force, or I'll tell you which way the force is, and I'll say, which way would the current have to flow? Okay. That might even, by the way, also make a good using principles of physics right to explain question. I could say, hey, what if I double the current? What happens to the force? Smaller, bigger, stays the same. Bigger, in fact, twice as big. Ooh, what happens if I, look. Actually, if I double the current in here, that can also change. That's a different current, though. Okay, I could maybe ask you some questions here. That would be a bit complicated. I don't know if I'll go there. Let us now move to the multiple choice, which I've said is going to be flogging right-hand rule stuff. And what I'm going to do is blaze through a bunch of older reviews that you haven't seen, and I'm going to stop at every single right-hand rule question that I can come across, starting with what used to be question number 25 from a provincial exam, but now I labeled it as number 1. We did this one, I think, already. What will the magnetic force acting on the coil cause it to do? Now, this is not a single wire carrying a current, creating its own magnetic field. It's not a solenoid. This is the right-hand motor rule. And you already said B because you remember this. But yeah, if you look at a charge on the top, on the very top, I have a charge moving to the left. I would point my thumb to the left. Magnetic field's into the, it's going to get pushed down. What about on the bottom? It's going to get pushed up. What about right there? The charge is moving up the page. It's going to get pushed to the left. What about right here? Charge moving down. It's going to get pushed. You know what? Everything's going to get pushed inwards. It would contract. Oh, by the way, number 5, this also would be fair game. This is just like the question we did, but instead of telling you the speed and instead of making you calculate its kinetic energy, I told you the kinetic energy. Well, if you know the kinetic energy, it's a half mv squared. Then you can find v because it's an electron, you know m. So a little twist to our standard radius instead of giving you the speed.
So the Teslas is just like to throw you off?
No, you need that for the magnetic. This is going to be FB equals FC. It's going to be QVB equals MV squared over R. You're not going to have V. Oh, yes, you do. It's hidden in kinetic energy. Right? So this was the first right-hand rule that we learned. This was the right-hand rule for a current-carrying wire. This is the magnetic field that a current creates. And that was you point your thumb in the direction of the current, right thumb, of course. Your fingers curl in the direction of the magnetic field. We used to have one more equation in this unit. It used to be the strength of the magnetic field around a wire, and the further you got away from the wire, the weaker the magnetic field, and it was an inverse squared, it was an over R squared. It's not part of the curriculum anymore. I vaguely remember it. I haven't even looked it up lately. All we're asking is, can you get the direction? And yeah, A. Right? There's the current.
Oh, okay.
My fingers curl this way, this way, this way, this way. It's that way.
Okay.
And it's that magnetic field that's created by the current. That's what interacts when we put an external magnetic field. That's why we have that force on a wire. It's those two fields interacting. That one. Sure, number 10. Here is a right-hand rule for a current-carrying wire. I've done most of these in the right-hand rules package that we did like 2 weeks ago, but I'm hoping you kind of forgotten them. Point your thumbs to the right. Okay. Well, you got to think about above the wire and below the wire, because that's what this picture is showing us. So imagine which way your fingers are curling above the wire, which way your fingers pointing or curling below the wire. I think above the wire, they're coming out of the page towards you, yes? And below the wire, they're going into the page away from me, yes? Am I doing this the right way? You guys are pointing, yeah. Would it be what? D, yes? Out of the page towards me above? Let me get a wire. So we'll imagine this meter stick is the wire, right? Above the wire, out of the page towards me. Below the wire, into the page away from me. All right? Right?
Oh, you weren't there for that. Okay. Imagine, you know, like what an arrow looks like? It's got the tip of the point on one side and it's got like two feathers there.
No wonder you're confused. Yeah. So this is to represent the tail feathers of an arrow going away from us. That's
So
the
if you
symbol
shot
for
an
into the
arrow
page.
looking at it, you'd see the
This is the symbol for the tip of an arrow coming towards us. It's a symbol for out of the page.
Trying to pick up.
You know what? That'll clear things up an awful lot right there. Trust me. Oh, you poor girl. No wonder. Excuse me.
It's a good thing you showed up to the tutorial.
Okay. So here's a right-hand rule on a moving particle. So now we're exerting a force. We have a beam of charged particles. It says they're positively and negatively charged. We're splitting them. Let's assume they're all positive. Point your thumb to the right. Gabby, what does that symbol mean? A magnetic field which way? So extend your fingers into the page, into my screen. Your palm points in the direction that positives will feel a force. Which way will they be deflected? Path 1 or path 2? Path 1. Which way will negatives, electrons, be deflected? Path 2. Okay. Oh, if it is an electron and they tell you it's an electron moving that way, well, an electron moving that way is the same as a proton moving that way. Our right-hand rule works for protons. You can do a complete new left-hand rule for electrons. Let's learn one and just flip it. Easier. Ah! Don't write it down, just watch. It says an electron enters a magnetic field as shown below. The path of the electron upon entering the field would be A, linear, B, circular, C, parabolic, D, hyperbolic. Which one of those is clearly, obviously the wrong answer because I've never used that word once this year?
D.
Okay? Every year I have a kid pick, no.
That's-
Hyperbolic? No, it's a
That's
hyperbolic. Yeah. You've done it in calculus. By the way, some comets we are looking for, so currently all the comets that we spot have elliptical orbits. An elliptical orbit means it doesn't have enough speed, enough energy to escape the sun. It comes around the sun, vanishes for a few hundred years, comes back, vanishes for a few hundred years, comes back. If it was parabolic, it would have exactly the right amount of energy to almost escape the sun. What we are looking for is a comet that has a hyperbolic orbit, because if it has a hyperbolic orbit, that means it has more energy than needed to escape the sun. That means it's from beyond our solar system. It's intergalactic. We haven't found one yet, but we're looking for the first comet that has a hyperbolic orbit. If we find that, that must mean that, remember the hyperbolic? There's nothing to do with what we're doing, but since hyperbolic appeared, that would mean that that comet was from beyond the solar system. It was
There's a
intergalactic.
picture about it. It's like two cones on top of each other and it's got all the grass in it.
Huh? Oh, the conic sections?
Yeah.
Yeah. That's calculus. Patience. Let's focus here. Look behind you. There's an attention span. Now, here, a lot of kids want to pick circular. It's wrong. Why? Try your right-hand rule. Which way is this electron moving? Which way is this electron moving to the right? Okay, we don't do it for an electron. Dorothy already flipped her hand. I love it. For an electron moving to the right, the same as a proton moving to the left. Yes? Which way is the magnetic field? Also to the... Which way is the magnetic field?
Right. To the left.
To the left. You cannot... You know what? This is why we said that force only exists when the direction of the charge or the current and the magnetic field are all perpendicular to each other. what really happens is a charge feels a force when it cuts across magnetic field lines. This charge is traveling parallel to the magnetic field lines. It will feel no force. If it feels no force, what path will it trace out? Yep. You got a question or are you done?
I've done an assignment.
Okay, can you stick it back there? Buxy, thanks. The correct answer here would be A, linear. It's obscure, but yeah. What I'm really testing is, do you remember that when we did these equations, we had little perpendicular symbols underneath all of them, even though they don't show up on your formula sheet? Okay, so here's a right-hand rule question. We want a force, Gabby, up the page. So here, I'm telling you the direction of the force up the page. We'll point our palm up the page. Which way is the magnetic field? What do these X's mean? Whoop. Which way must the current be going? Okay, that would be the direction. And if I was answering this question, I would say put a check mark next to the right. No, yes, no, pointing that way. So I would cross out B and I would cross out D. Now I want to find the current. I'll use F equals Bill. I'll solve for I. Which length will I use? This length, or that length? They've given you 3 different lengths to try and confuse you. The 0.22, the section of wire that's inside the magnetic field. Okay? Yeah, we saw this a few minutes ago. I only have so many of these graphics, and they're hard to make, okay? Fine. But they are. Okay. I have not done any of the right-hand rule questions from your review because I think you need some practice on your own. Sorry?
Can you do one with the solenoid?
Sure. The only way I can, I think I'm going to have to draw one. Okay? And it gives me an excuse to draw a solenoid. Yay. Pen. Why don't you go down lower? Oh, there you go. Now you are. R stands for what? Right-hand rule. Solenoid. You can watch or you can draw this one with me. To draw a solenoid, I sketch a rectangle like that. And the trick to drawing a solenoid is you do long, elongated S's. That makes it look kind of three-dimensionally. You can also do backwards S's. Yes, they are little integral signs. Thank you. You made my little math nerd heart go pitter-pat. And I'm going to have it come down the front of the solenoid on the left. And I'm going to... Oh, I need a battery, Mr. Dueck. I'm going to leave a space for a battery. And I'm going to have it go underneath the solenoid on the right. Okay? I don't know yet. I haven't told you which way the current's going. Okay? And just for giggles, let's have the battery going dunk, dunk that way. Okay? And then we'll change it. We'll flip the current around going the other way. But for now, that means that if I follow the current that way, that way, that way, that way, yes? That's it. Question? I haven't done the right-hand rule yet, but do you see where the red arrows came from? I'm imagining the current flowing through. Okay. Now, here's how the right-hand rule for a solenoid works. Pretend you're holding the solenoid in your hand. Do it. Okay? Right hand. Now, before you figure out, we don't know yet, here's how you figure out which way to flip your hand. Curl your fingers in the same direction as that current, as those red arrows. Ah! Your thumb points north in the center of the solenoid. Which way is your thumb pointing? To the left or to the right? Okay, so for me, that's north, that's south. Now, you got to be careful because magnetic field lines go from north to south. If I follow the magnetic field line like this, it's pointing to the left inside the solenoid, but outside down here, which way is it actually pointing when I get down to there? To the right. Right? Right. No, right. Okay. What if I, and this is why I drew this way. I hope I can do this. What if I don't? You laugh. I fix this. What if I don't? Really? Really? That one's being stubborn. There we go. Nice try. What if I flip the current? Okay, now, and by the way, whenever you give me a solenoid, I have to sketch those arrows on there. Otherwise, I can't do it. It's the easiest way to keep track of the diagram. So you gave me a solenoid. Now the current is moving this way. It ducks underneath, and it comes down this way, yes? Okay. Hold the solenoid in your hand. I'll come back to your question. Curl your fingers in the direction of the current. Your thumb points north in the center of the solenoid. In other words, the magnetic, which way? Is your thumb pointing to the right? Yes?
Yeah.
The magnetic field inside the solenoid points this way. That would be south. That would be north. Oh, and again, if you follow this all the way through and around, though, eventually on the outside, below and above, it ends up pointing in the opposite direction. But inside the solenoid, this gives us our magnetic field direction. Dorothy, did that okay?
Yeah.
That's the solenoid rule. Oh, instead of giving you a horizontal solenoid, I give you a vertical solenoid, but just hold your hand like this or like this. And in fact, that's what we did today. We made our loudspeakers, right? We were taking advantage of the fact that we could flip a magnetic field, and if we had a magnet above that magnetic field, that meant that magnet would be alternately repelled and attracted. We would do that, and that's shaking that lid, sending vibrations to the air. Oh, and we got clever as our power source, as the I part of B equals mu naught Ni over L. We just made sure that that power source was actually coming right from my speakers, which means the current is directly proportional to whatever the sound was doing. It takes care of itself. You saw it was able to mimic the vibrations appropriately, perfectly. Well, recognizably. Say that. Okay? So that's the solenoid rule. So the three right-hand rules: current carrying wire, that's when you have a wire and no external magnetic field. And there will be one like that on your test. And I'll say, hey, what direction is the magnetic field? Hold the wire, point your thumb in the direction of the current, fingers curl in the direction of the magnetic field. We started out with that because the other two come out of there. If you actually sit and think about it, what this really is 1, 2, 3, 4, 5, 6, 7 wires side by side. This wire on this side has a magnetic field into the page, but on this side has a magnetic field out of the page. It cancels out there. If you add up all of the magnetic fields that don't cancel out, the only place that they don't cancel out in a solenoid is a nice tube down the middle. So it comes out of the right-hand rule for a wire. Oh, and then the third one, that's technically what's called the vector cross product. In fact, I think I told you it's also the rule for a screwdriver. If you want a screw to go down, you turn it that way. If you want a screw to go up, point your thumb up, turn it that way. It's a torque. It shows up all over the place, not just where we have, and you'll do a lot more of it if you take post-secondary physics. Okay. Let's try a few more right-hand rule-ish questions, or have I used them all? I went through the newer one, I'm at the bottom. I went through the older one, I'm at the bottom. You know what? I think I'm kind of...
Can we do one with like an electron and a proton
where you switch it?
You said that's the opposite way for an electron.
Heck, let's look at your actual review. This is the one that I gave you, right, Mr. Dueck? Yeah. See if I can find one here. So, number 5, what's moving? Which way is the electron traveling in all 4 pictures? See it? To the right? We don't deal with that. An electron traveling to the right, the same as a proton going which way? To the left. So point your thumb to the left. and it says, which of the following is not a possible pathway? Now, number 1 is weird because I noticed that the magnetic field and the path of the electron are parallel. You know what? It'll keep going in a straight line because it's not crossing any magnetic field lines. Number 1, this is like that trick question I showed you a little while ago. Number 1 is a legitimate path. But what direction, what do these dots mean, Gabby? What direction is the magnetic field here? So electron this way, proton this way,
So you
out of the page. Which way would a proton get pushed? Which way will electron also get pushed then? Up. Is it getting pushed up? That's possible.
So you do these questions with the electron as if it was a proton.
Pointing in the opposite direction. Yeah, you pretend.
So if it was a proton.
Proton moving up, that's a, sorry, electron moving up, that's a proton moving down. Electron moving left, that's a proton moving.
Right. But so.
Nothing else changes.
Yeah, but if it was a proton, it would just be, you wouldn't flip it.
If it was a proton, I wouldn't flip it.
Yeah.
Okay. Electron moving right, proton moving left. Which way is this magnetic field? What do X's mean?
To the page.
So
Down.
it's going to get pushed. That's possible. And this is a tricky one. This one is not possible. Yes, it would get deflected down, but the radius wouldn't start to change. It couldn't possibly spiral because if you look at that equation where we got the R by itself, I think it was mv over qb. The m's not changing. V's not changing. Q's not changing. It's in the same magnetic field. This is a tricky one. The radius can't possibly be shrinking. The only way that that could be the case, where you could have it kind of start to spiral and get to a smaller radius, you'd have to either slow the speed or bump up the magnetic field or something like that. Yeah. So that's a tricky one, but it's got 4 pictures, which is what I kind of wanted. Remember, flip it for electron, right? I'm going to go try another one. Here's a good solenoid right-hand rule question, such that I'll even cut and paste it. Because you were asking for one, and I said I couldn't think of one. I just saw one here. Boy, this thing is... Oh, that's because I'm zoomed into 200 times. No wonder. There, now that'll fit. A bar magnet is at rest. Let's imagine it's hanging by a thin thread, so it's free to rotate. When the switch S is closed, the bar magnet will move left, right, up the page, down the page. Let's close the switch and let's draw in the current, because that's a solenoid. Yes? You with me, Dorothy? So when I close the switch, here's the positive, so the current is going to be going this way. Yes? This way, this way, this way, this way, this way, this way. So hold the solenoid in your hand. Curl your fingers in the direction of the current. Can't possibly do this like this. That's a guaranteed F. Hold the solenoid in your right hand. And by the way, you notice I'm not raising my hands on purpose because I'm forcing you to figure this out. Curl your fingers in the direction of the current. Let's see. It looks like they're curling over the top. Yeah, you're right, Dorothy. I have to hold it like that. Which way is my thumb pointing? Left. That's the north pole of this solenoid. I would put an N there and an S there. Now, how will this magnet react? What will this north pole... What? So what direction will it move? It will be repelled. It will move to the left. Or if it was free to spin, it would spin around so that the south pole was close and the north pole was being repelled. But they didn't say that I was able... They didn't say there was a thread here. Yep. It's not going to move up or down, I'll tell you that. Okay? And what you really have is, power door locks. Flip this vertically, okay? And put a magnet on the bottom of your lock, and now you can attract. Now your power door lock has gone down. Repel. Now your power door lock has gone up just by reversing the current in this switch. I don't know if they work via solenoids. I need to take apart a door one of these days from an old junker car and find out.
You need a current for the solenoid though? And if the car's off, how does it do that?
I don't know. When your car is off, do the lights go on the interior still?
I guess a battery.
Yeah. Yeah. Is it good to go, as a little kid wants to do, unlock, lock, unlock, lock, unlock, lock, unlock? Probably not. You're taking some power from your battery. But yeah, your car has, that battery stores a fair bit of power, right? I mean, newer batteries, I've rented cars where lights have been left on with the interior light we forgot was turned on, and because the previous customer left it on, where it was left on overnight, and we were fine. So left it light on for about 14 hours. In fact, I think in Phoenix we had it on for about 2 days because you couldn't tell it was on during the day because it was so bright, and we never drove anywhere at night. I only noticed when I brushed against it, "Ah, that's hot!" Oh yeah, it had been on for a couple of days. So, yeah, the newer batteries are pretty good. Couple more.
But if you're not driving, one car.
So here is a right-hand motor rule question. This is tricky, but here's what I want you to notice, and I'm going to have to kind of shrink this down to get it all on one page here, a little bit more. This was a graph interpretation question, and this was the year it came out, one of the toughest questions on that year's exam. As current gets bigger, what happens to the force that the scale reads? It increases, which means that it's feeling a bigger force pulling which way, looking at this setup, up or down, if the scale is getting bigger?
Down.
Okay, which means the force on that section of wire is which way? Down. Let's point our palms down. Which way is magnetic fields? Always point from what to what? So I've got to rotate my hand around like this so I can point from north to south. Which way must the current be going in that section of wire? It's got to be going to the right. If they asked me to sketch this circuit, I could say that's the positive, that's the negative. It's got to be going this way. I don't think they did here, but you're looking for right-hand rule practice questions. There's going to be some kind of a question like number 9 where I ask you to identify a magnetic field lines question. Oh, nope, that's wrong. Fit width. Okay. Here's a right-hand rule question. Try number 10 if you haven't already. Try number 10 if you haven't already. In this one, they're telling you the direction of the force, so you have to figure out which of those diagrams would work if you know the force. I can't do these in my head. I have to do the right hand. So what direction is the force, Dorothy?
Out of the page.
So point your palm. If you want to use this, then point your palm like you're looking at it, because that's out of the page, yes? Which way is the current in all 4 diagrams? So point your, because that's not changing, point your thumb to the left. Which way must the magnetic field be for you to get your palm facing out of the page?
Oh, is this over here, like here?
No?
B.
Let's see. So in Dorothy, in all 4 of these, which way is the current?
To the left. No,
Point your thumb to the left.
that's not.
Which way do we want the force? Out of the page? So for me, I got to bend like that.
Yeah.
Which of these tells me the magnetic field? My fingers. Which way are my fingers pointing?
Down.
So which is the correct diagram?
Remember?
Yeah.
F, right here.
Which is the correct diagram?
D.
Okay, that's.
Dorothy, which is the correct
Oh,
diagram?
D.
D.
So F is. Oh.
Force is palm.
B is the fingertip. And I is
Magnetic
the thumb.
field. So it's thumb current. Fingers like you're high-fiving, because I had to. A lot of kids were doing this, Gabby, and that was pointing your fingers. No, you just added a 90-degree angle. Fingers like you're high-fiving. Palm points in the direction of the
Except for if
force.
it's a wire.
That's a different right-hand rule.
Yeah.
There's 3 right-hand rules.
And how do you know you're not holding the wire?
Read to me the question, the whole question.
In which diagram would the current carrying conductor experience a magnetic force out of the page?
Here's how you know. Look at the pictures. Do you see that there is a wire and there's an external magnetic field in each picture? That's the right-hand rule when it's a wire with an external magnetic field. The one where you're holding the wire, what they'll say is, what is the force caused, what is the magnetic field, my fault, what is the magnetic field created by or caused by the wire? Here, they're not telling me or asking me about the force caused by the wire. By the way, they're using a similar picture, absolutely, because they want to see, do you understand the difference? It's tricky.
So, but they'll specify if it's a wire in the question.
Yeah, it'll be pretty clear. Hey, number 11.
Because the current is not.
Ready? Here's another right-hand rule question. It says, when current flows through this coil, the tension in the thread is, what's the word right there, Diana? That means which way is the force in this coil if the tension got less? There's tension. How can I make tension less? Gabby, up. Does that make sense, right? Normally gravity pulling down, it says tension was reduced. That must mean there's an extra force up. That's the direction of the magnetic force. Now, what is the force in my right-hand rule? Palm, up. Ooh, Gabby, which way do these X's mean? So not like this, but like this. And the section of wire that's perpendicular to it all is this one. So which way must the current be flowing in that bottom section of wire? And up, and left, and down, and right, and up. You know what? I think is the direction they look for counterclockwise? Counterclockwise? Yeah. I haven't told you how to find the magnitude, which is the other part they're looking at. 11's tricky, by the way, because when you find the magnitude of the current, you're going to want very much to pick D, because the current is 4.1 amps. That would be if it was one wire. How many coils does it say there is here? This was nasty. I saw the results for that exam that year. I think 80% of the kids picked D because they were so proud. They got the direction counterclockwise, and they went F equals Bill. They solved for I. What number is this? 11, right? Let's go find it. Oh, I thought this was, I mean, I thought it was okay. It was cheap, but good, pay attention. It was, oh, I found the current, everyone gets that, and you get 4.1, and like, oh, it's 4.1. Ah, wait a minute. How many turns of wire? How many wires are there? 25 wires. So you know what? Since you got 25 separate wires, not one, you can divide that current by 25. It's going to be 0.16 amps in every single little wire there. Which is sort of what we were doing with more turns in that solenoid in today's loudspeaker, for that matter. It was a way to get a bigger magnetic field or a bigger force. That was a sneaky one. Yeah, but I was okay with that. Something like number 13. How do I know which one's north, which one's south? L or R? Pardon me? I didn't hear. I think you're right.
I said north to south.
North to south. So you look at the arrows. North must be R. South must be L. By the way, which way would a compass point? A compass points from north to south. By the way, what all a compass is a little north pole on the end of a stick. And a north pole wants to point away from the closest north pole and to the closest south magnetic pole. Magnetic field lines are also the same direction that a compass points, because a compass is a little tiny magnet. And yes, that means that up at the north geographic pole, there is a great big south pole there. And in fact, I think I gave you in your notes on one of the last days the dumb joke, right? Where are we? Block B.
Oh yeah, the one with the big solenoid.
Yeah. The Earth is a magnet. Where did I do the solenoid? Oh, I think it was...
The one with the big solenoid currents.
Yeah. Ah, there it was, right? Yes, of course I'm sure this is the magnetic North Pole. Who the hell left that great solenoid here? Yeah, the Earth, kiddo, is... is this. Okay? This is what the inside of the Earth looks like. The S of the Earth's magnet is up there. Tilted, because the Earth has a tilted axis. I think I have a better one that has the tilted axis picture.
The points there at the end of the magnet, is that what makes it like a circle?
No.
The magnets we work with have a
All
straight edge.
no, the magnets that we work with are they all magnetic field lines curve, and you're asking me why, and to my chagrin, I don't know why they curve. I know that they do. Sure. We have yet to develop technology, and right now I think we think it's impossible to separate a North Pole completely from a South Pole. We think right now that they have to exist in pairs, which means as soon as you have a North Pole, you must have a South Pole somewhere in its vicinity, which means that magnetic line of force wants to find that nearest South Pole, so it's going to curve every time. I think that would be my answer. Yeah, okay, I'm okay with that. Sure. I thought I had a better picture of the magnetic field inside the Earth. Oh, I think I had it in your notes. I had one with an Earth's axis tilt. Yep. Let's go back to our tutorial, Mr. Dueck. Tutorials. Bit more right-hand rule stuff. So I think most of you are okay on the written section. You need to practice it. And again, go through the review. The only surprises you might find is, oh, that's the same question, but he's going backwards instead of forwards. In the review, he gave me the question and said, find the answer. Here, he's giving me the answer and saying, find one of the pieces of information I needed to find to do the question in the first place. Right? Did that one already. In terms of cathode ray, I think cathode ray is actually going to be on your next test, even though I covered it here. Oh, here's a nice question. A good right-hand solenoid rule question, okay? So here is a magnet suspended on a thread, so it is free to rotate. It says the diagram shows a magnet suspended near the solenoid. After the solenoid has been connected to the power supply, the magnet rotates to a new position. Let's cut and paste this because this is a big diagram. So when we flip this solenoid on, look at this picture. What happened? The South Pole moved how and the North Pole moved how? Can you use a word attracted or repelled in the word South Pole? The South Pole was, and then fill the blank in, attracted. What would attract a South Pole? You know what? There must be a North Pole there and a South Pole there. Magnetic field lines always point from what to what? So the direction is from 3 to 4. From 3 to 4. What would give you a North Pole there? Now I'm going to imagine holding that solenoid in my hand. I'm going to imagine holding that solenoid so that my thumb points north. Which way are my fingers curling? Direction 1 or direction 2? Which way must the current be? Direction 2. So C. I hope the answer is C. Is that what I said in the back for that one? Yep. There's a nice question. If I could find a way to do graphics like this, I totally would, but that there looks just like hours and hours and hours of work. I don't care about you guys enough to do that. No, truth. Now, you were asking about the what if it's a single wire, okay? 21. Looks almost identical to that question we looked at, diagrams we looked at a couple questions ago. Read it to me in a big loud voice, please, Dorothy, because I want to teach you the trigger words. Go ahead.
Which diagram shows the magnetic field created?
Stop. The magnetic field what?
Created.
Created. This is not an external magnetic field that something else is putting into the diagram. This is the one created by the wire. Keep going.
On near conductor carrying current towards the right.
So the key idea here is this is a magnetic field that's been created by the conductor. That's when you point your thumb in the direction of the current and your fingers curl above and below in the direction of the magnetic field.
So
It'd be
D.
let me see. Yep. Yeah. Yep. Yep. Gabby, that's okay. You see the subtle difference in wording there? Okay. Other synonyms, caused by instead of created, induced by.
So created, so wires and solenoids create magnetic field?
Yep. A wire, if I run a direct current, it will create a magnetic field. All wires are automatically magnets. In fact, electricity and magnetism are part of the same force, Dorothy. It's much more complicated than that, but that is a true statement. In fact, we call it electromagnetism. For a couple hundred years, people thought they were separate, but in the 1880s, they realized, oh, same thing. Act differently in different ways on different objects. The same thing. Can't have one without the other. Oh, here's a right-hand solenoid rule. 24. There's a solenoid as shown below. What's the direction of the magnetic field inside the solenoid? Look at the direction of the current. Add the arrows to your diagram so you can really visualize. I find it helps. And see, I think the current's coming over the page towards, over the solenoid towards us, yes? I think the magnetic field is pointing A, yes? This is really tough because I have to reverse every diagram if I'm doing it so you guys see. Tougher than it looks. By the way, to do this honestly, drawing 5 or 6 arrows on the solenoid, then it's more obvious which way to curl your
Oh
fingers.
no, I was using my left hand.
Oh, don't do that. Don't do that. Dorothy, can you read 26 to me, please?
Which of the following diagrams best shows the magnetic field due to a strong...
Stop. Due to, caused by, created by. So another, okay? That's the key difference.
Well, it says Y.
Okay. Pardon me?
It says Y.
But still, there's other diagrams with wires in them. If the magnetic field is external, like here, that magnetic field is not caused by the wire. That's an external magnetic field. We want to know the force.
Are you left-handed?
No, she's just
I think
silly.
The first thing you should write when you get your test is use right hand.
Put a big L in marker.
I can put some rings on my right hand.
There you go. I said in one block, I'll say it again. 33, that's actually a torque question. You can't even do that. I haven't taught torque with you yet. 34, I mean, you have the skill. This is similar to that number 9 from the written that you had to find M and use M to find M twice. There you go. So any other questions? Let me hit save, and then I'll hit print.